many of you are scientists, right? The media always say, you only want to do research. You always say, you give me an answer, but say, we need to do more research. And that is something that we hear all the time. So it's very important that you still bring that across. We need research, but we can also give answers. We try to give answers in a certain uncertainty. And you would need to help policymakers, politicians, to understand that and help them trust you. They have to trust you. If they don't trust you, they're not going to listen to you. That's something that over all the years that I've been in the business, I've learned how important that is. And my story is a little bit about those things. I also always like to make a little comparison of my country and other countries, because the problems in my country are the leading theme in my presentation. But of course, I mean, that's a local thing, right? And so we have to transfer the knowledge that we have from our own environment to other environments, and especially give the differences. One of the things I've really enjoyed doing is working in Vietnam, and part of that was advising the Vietnam government on the future of the Mekong Delta. You see the Mekong, there's a pointer here. You see the Netherlands over here, so the North Sea is here, UK is about where I stand here, and so this is an enclosed sea, the North Sea, and the Netherlands runs something from here to here, and here is the important main river that we have, the Rhine River, and the Meuse over here, and basically this is a delta, and half of the Netherlands is Holocene material. After the last glacial period, half of the Netherlands wasn't there. In the interglacial, in the Holocene, half of the Netherlands was created by sediments being brought in by the tide and by waves. If you take the Mekong Delta in Vietnam, so here is Cambodia, and Vietnam goes all the way up here. This area here is completely formed in the Holocene. It's all Holocene matter. So after the cold periods, it wasn't there at all. About the same size as our delta. There's some differences and some similarities. The similarity is something I couldn't believe. We think the Netherlands is a densely populated country, right? You know, 17 million people. Dave has lived there for a while. We've always been taught on primary school, we're the most densely populated country in Europe. The Mekong Delta, of which 1/3 gets completely flooded each year, has 17 million people in it. It's as large as the Netherlands. So that's really also very heavily populated, only they have much less space where they live. So they're very much concentrated. We have many similar problems, like salinity intrusion, subsidence, agricultural problems because it's salty, you name it. We'll talk about these issues that are similar. Back to the Netherlands. Now I told you half of the Netherlands wasn't there after the last glacial period. And actually you see here the bathymetry after the interglacial started. So the earth started to warm up, right? And so at the coldest moment, the water levels were like 50 meters lower than current mean sea level. So England wasn't an island. You could just walk across and the mammoth would be there on the North Sea bottom. Our dredging companies, when they bring sand to the shore, they find mammoth teeth and all these things. So basically this was dry after the cold period. And so if mean sea level would have been at current mean sea level, the shore would have been here. And so Amsterdam over here has a Holocene package of 18 meters. And so that has all been filled in over time by Holocene material. And that shows you also the vulnerability. Because if you look at the current topography, I could talk hours about how it came to being, but in short, the story is that tides originally, when the water levels were not that high, so it was something like 1, 2, 3, 4, 5 meters of depth over here. Waves weren't that important, and the tides brought in loads of sediments. And it filled this whole area because it was protected. And then at higher water levels, the waves started kicking in. And they formed barrier beaches over here, like you have a lot here on this coast. And they formed barrier beaches, and behind that, lagoonal systems, like you have a lot here as well. Only in the Netherlands, we've closed them all off. We've made them dry, because we need a space to live. So that's why you have here areas as deep as more than 6 meters below mean sea level. People are very comfortable living there, because the polders are reasonably protected, as I will show you. But part of the depth is also subsidence. We have had more than 2 meters subsidence on average in those areas. Luckily enough, this took us 200 years, so we got adjusted to it. Many places on the world now, especially the mega cities, in Asia especially, they subside maybe as much as 10 centimeters per year. 10 centimeters per year, right? We're talking about mean sea level rise per year. You can hardly see it here, right? 10 centimeters per year. We got it. It took us 200 years. Jakarta, that's happening in 20 years. So we face problems there in that we have to take strong and immediate action. Same in Shanghai, same in Bangkok. You've heard about the floodings 2 years ago, very same thing. So basically, your static sea level rise currently is not the worst to take into account. It's really the subsidence that is the problem. Also for New York. It's not sea level rise eustatically. It is what we do in the underground. Also building all these high-rise buildings. What do you think that weight does? You know, you just sink. So that is something we have to deal with. And also a political aspect there is that in Asian countries, the governments don't like to say that it is sea level rise. That it's their own fault. They love to say it's sea level rise, because then they knock on the USA door and say, look, you guys, you change the climate. You have to help us solve our problems. But it's the local problems that are really there. So it's a very political issue as well. Just one number to highlight. That is that you see here the liability to flooding of our country, which is 59% in surface area. Maybe you remember that IPCC had loads of problems last time when they were accused of making mistakes. One of them was this number, because they said 59% was due to flooding due to sea flooding, which wasn't true, because it was also river flooding added to it. But this shows you how careful you have to be if you present data. Always make sure that you're correct in your data. You may not think it's that important, but they can just kill you, you know, if you make a mistake. And then something that many engineers in my country have been very proud of, and that is the principle of shortening the coastline. But lately there's a bit more discussion about it. Let me first point out the advantages. If you look at our country, more than 1,000 years ago, we had a very long coastline. Everything which is orange here is like a coastline. The same as if you look here in Chesapeake Bay with all the estuaries. Your coastline is amazing, because you have all these estuaries, and that's all a transition between the sea and the land, right? And so if you have to protect this, you have a lot, when it's too weak, you have a lot of shoreline lengths to protect. And so if you shorten your coastline, for instance, Here up in the north, the monks did a lot of work to close these estuaries. What they simply did is they promoted sedimentation, and then once it's sedimentated enough, they put a dike in front of it. And so you really, it's like taking one of your estuaries, promote sedimentation, and then close it off. And I've seen Dave's nice location. He's on the estuary and has his boat at his house, so you don't want to lose that estuary, right?
No.
But in those days, I mean, that was a very, very handy way of trying to save costs in safeguarding you against flooding. And in the 1800s, they'd done quite some work here as well. And then in, it's hard to see, here 1916 flooding in Amsterdam. Amsterdam is over here. Some of you probably have been in Amsterdam. Like Schiphol is on -3.5. And there was a lot of flooding from the time that this dike wasn't there. And that dike was built after the flooding in 1916 because it flooded large parts here, over here. And that has created a lot of advantages, like this is a freshwater basin now. We have reclaimed a lot of land there, which was good for agriculture, which we learned from the Second World War. We didn't want to be dependent on importing products from abroad. And so that principle, and the same thing happened in 53, when we had this large flooding, and we closed off many of these estuaries. And that's basically using the principle of shortening the coastline, which makes it much more affordable to safeguard against flooding, because you have a much shorter shoreline to defend. It has disadvantages as well, though. We'll talk about that later. It would have been, and then I always tell my students the example of New Orleans, that where the water boards refused to move these water pumping stations in these marshes in New Orleans towards Lake Pontchartrain. No, they kept them over here. So they had canals which were flood prone because Lake Pontchartrain would just deliver water to the canals. And I don't have to explain to you what happened. The canals, although the defense was high enough, they weren't strong enough. And so on several places, they breached. Had they had a much shorter shoreline, could have been prevented. But that was a matter, of course, of weighing the interests. And I know in the States, one of the problems is that, like one of my colleagues, Jay Lund in California, always says, the Americans hate government so much, they have thousands of them. And so it's very difficult here, I know, to come to a multifunctional solution because, well, all the parties that have an interest, they're not that flexible. And I know why. It's not easy, you know. The politicians love to say, we need multifunctional solutions. Well, you try it. It's really very difficult. And here's another view. This was pretty safe over there, right? Because that was actually on the banks of the river, the elevated banks. But this was the marshy area. And that was basically a polar that deserved a lot more protection. We'll make a little step back to New Orleans again. This is just telling you, one of the red threads in my presentation is that I'll tell you about what a new Dutch committee did in advising about the problems that we have. We called it, there wasn't a flooding, because all the committees we had were always after flooding. You know, something has to happen, and then there's action, right? In the Netherlands, we had a good minister, a woman, which I think is one of the reasons why, that said, look, nothing has happened, but I feel after like a warning, like we got from New Orleans, that we need to revisit our view on our vulnerability. And she had the courage to establish a committee and say, you review again the situation in our country, and I want you to advise me on whether we are geared for the future. So that was really a courageous decision. And it was the so-named Second Delta Committee. She had, however, only looked at sea level rise, and she asked us to look at are we safe against flooding from the sea, especially in the coastal regions. So we came together as a committee, and in the first hour of our meeting we said, look, that's too restricted an assignment, you know. It's not just about flooding. We get water from the rivers. We don't know what the Germans will do in terms of retention, so that'll change. We have changes in rainfall. We have salinity intrusion. We have many points where we take fresh water from the system. We have subsidence. So we need to look at the whole water system as such. So we made a call after an hour to the minister, please give us a broader assignment. Let us please look at the whole system. And she said, great, you're fine, you can do it. And so we mapped all the problems we had, and we made an assessment in the end. The report is on the internet, and it took us only a little over a year. I'll tell you a few things about it. There's 3 steps that politicians need to make. I'll explain that to you. And we advised on a higher safety standard. Something we did, which gave quite some discussion, is that we didn't only look at the average scenarios, but also at the high-end scenarios. Because, you know, if you're faced with a high-end scenario, you have to take that into account. Of course, not the highest probability, but if it is probable, then you might as well take that into account. You know, if in 200 years our system is unsustainable in a high-end scenario, we should now try to make very good friends with the Germans, because we need a move up there. And so we really wondered, can we hold it the way we do it? And then we converted that into a recommendation, and I'll explain a few to you. When we presented the report, then our chairman said to the minister offering our report, do we have an acute problem? No, you can go sleep. But do you need to do something? Yes, you do. So it is not acute, but it is urgent. And one of the things which had been frustrated me and my colleagues for a long time is that after the '53 flooding, standards were set and cast into law about what the level of safety should be for the different regions. And actually, until today, not even those levels are sustained. So all to do with money, right? And so the first message was, before you change anything, do what's in the law. Obey the law. You know, we have a yearly check of our cars. If you buy a car, you get it yearly checked. If I bring it to the garage and they say, look, sorry, need a repair, they won't give it to me until it's repaired. The government checks the flood defenses and concludes, well, 30% is not okay. So that was a simple message. Please do what's in law, number 1. Second, if we look now at the system, with new eyes, should be safer. Factor of 10 safer. And take into account that climate change, there's always been climate change, right? People talk about climate, but climate change, that's always happening. The question is, how much will it accelerate? And the good news is that the ocean system is very slow. You know, we can just monitor, and if it goes faster than we expect, we can respond because we have the time. If it goes slower, we don't need to respond. But you have to take it into account. The number 1 principle that we adopted was already established by the first Delta Committee in 1960. And that is the so-called risk approach. where you use the principle of economic optimization. And the simple presentation of it is that if these are dollars, right? This is what you spend. And this is your safety level. So it increases from here to here. So the more you invest, the more you invest in your safety, and so the more dollars you spend in your safety, the more reduction you have in your damage costs, right? So the safer it is, the less often you'll have flooding, so the less often you will have costs because of the flooding. And the sum of those two is this drawn line. And the minimum is over here. So if you invest enough to reduce substantially your damage costs over the projected probability of occurrence, then you reach a minimum. And that is minimal societal costs. And that principle, we think, is a very strong principle and should really be adopted all over the world. Because that is what you would call a sustainable solution. You minimize costs for your and future generations. Our estimates is, this says New Orleans before Katrina. They were around here. So their damage costs were really much too high. And they've told me about a project, $125 million, right? Something like that.
Hurricane protection project.
Right.
Virginia Beach. Right.
Yeah, hurricane protection project. It was the 1 year storm that you got after that?
Well, it was Hurricane Isabel.
It was Hurricane Isabel.
That same fall.
And that Hurricane Isabel cost $80 million.
Saved $80 million
of
damage that would have occurred without the project.
Right.
So in one storm, it almost paid for the whole project.
Yeah. And so I don't know more detailed numbers, but you could cast that in this form, right?
Right.
And I imagine Isabel is like the 1 in 20 year?
Oh, even worse. It's even higher.
Okay.
1 in 50 maybe.
1 in 50.
Yeah.
Yeah. But over the projected lifetime, you would also have to look at the 1 in 100 year storm.
Oh, yeah.
Yeah. And all those smaller storms, right? And so use this principle. This will minimize the cost for the society. You'll still have the costs. I mean, it's impossible to make something totally flood-proof. That's something also, statistics you have to explain. Our chairman, he's a very clever guy, but it took me an hour to explain to him, you can't make something 100% safe. That simply doesn't exist. And he's a very clever guy, but it took me an hour to explain that to him. And sometimes I think he still doesn't believe me. But he trusts me, so that's all right. And so that principle adopted to our country, and so you recognize this maybe as the flood-prone area, has led to a varying safety per area. And so this is the area of South Holland and North Holland. Amsterdam is over here. Here's The Hague and Rotterdam and Delft, not to forget. This is where we have the largest economic activity, the largest number of people living. And so actually from the principle of economic optimization, a safety level there is chosen of 1 in 10,000 per year. So those areas should be able to withstand a 1 in 10,000 year event. Sounds pretty extreme, right? But it's not that extreme. You know, if you look at, if you go from 1 in 1,000 to 1 in 10,000, then you talk about storm surge levels which increase about only 1 meter. And here I estimate half a meter for every factor of 10. And so the river areas are the least protected, so 1 in 1,250. There's another reason behind that. That's because certainly in the Netherlands, river flooding is more easily predicted. because the discharge wave on a large river travels, of course, slowly and can be monitored, and you can predict much better than sea flooding. And so, actually, in the 90s, we had 2 times that in these areas people had to be evacuated. But very interestingly, that a empirical figure is that the probability of the no, sorry, I should first say that in this assessment, which was based on the first Delta Committee after the 53 disaster and the 1960 report, this didn't take into account loss of life. In those days, society was not ready to value life in monetary terms. Now we do. In our country, a life is about €1 million, and there have been developed, of course, group risk scenarios. So when petrochemical industries may, or a plane may fall down, you know, there's a lot of assessment done, and one of the assessments is that the individual risk in our country that you run as one person to die due to external cause is 1 in a million. By the way, every year you have a 1 in a million probability that you die because of an external cause. And in these green areas, we know that if a flooding comes, that there's a 1% probability that you don't survive. That's an empirical figure. Our 53 data are like that, but New Orleans as well. If I remember correctly, I think 200,000 people in New Orleans did not evacuate, and of those, 2,000 died. Again, 1%. So it's 1% that is not able to survive due to a flooding. And so actually in those green areas, you have a 1 in 125,000 per year probability that you die due to flooding, which is a bit amazing, you know. I mean, they force oil companies to make refineries so safe, and train companies to make trains so safe with chemicals that people only have a 1 in a million chance to die. And here the government tells you, oh, look, due to flooding, it's 10 times less, which is a bit strange. Governments can do funny things. Yeah, and then in the context of optimizing safety standards, well, many of you will realize risk has to do with the probability that it goes wrong and how much is being damaged. You know, if nothing is damaged, then probability can be high, but there's very little risk. So it's the combination of these two. And I'll talk a little bit about how the insight in probabilities has changed, but also how the insight in damage has changed. And one of the things that in my country that we were looking at since about 12 years ago is piping. And so here's a fault tree of everything that can go wrong when we talk about flooding. So the probability that we get flooding is determined by the failure of a dike system, a dune system, or a protection system. Here's floodgates over here. One of the most points of attention that we had was the piping problem. You may know the piping problem in dike systems. That is that dikes are usually made of clay and organic material, but there's also sand layers in it. It may be quite inhomogeneous as well. And very often you have these little sandy channels. When there's a lot of water pressure on it, the water runs through these channels, and the sand is easily mobilized. And actually then you get a well on the inside of your dike system where the sediment comes out with the water. And 12 years ago, when we got into this problem, it was very hard for us to convince our authorities that we should look seriously at that problem. And well, here's many other things that can go wrong, but especially a piping problem I want to show to you, because in New Orleans, in that sense, was heaven for us. Because in New Orleans, the failure of those walls was actually due to piping. You see here, you see a sinkhole on the inner side of the vertical wall on sheet piling, and this actually caused the failure. So the walls were high enough. The water level didn't come over the height of the wall, but the walls failed due to these type of problems. And in our country as well, there was a lot of attention simply for the levels. Would the levels be higher than the dike height or the quays that defended them? But you really need to take into account all sorts of other problems. And like I said, that New Orleans in that sense was very bad for the people, but it was very good for us to tell the policymakers and the government, look, it's not only how high something is, there's all sorts of other things. And here, I don't know if some of you recognize this, but this is the airport of New Orleans, the small airport, is just outside here. That was outside the primary defense, and there was a wall connecting to the whole defense system. Only there was part of the wall never built. So, although this wall was high enough, the water just came through it because it didn't exist, that wall. It was just forgotten. And I don't know if you also remember pictures where they had floodgates. The floodgates didn't close. They didn't close the gates. And something that I never could believe, but one of my famous professors always told us, be aware that you pay enough attention to the connection between a structure and the earth body that connects to it. So here is like a sluice gate. This is Lake Pontchartrain, and here is the structure in concrete, and it just got eroded here at the backside. So it's simply that the connection between the dike structure and the concrete structure was not correct. So this is like a textbook example that I always thought, who's going to be so stupid to make that mistake? It happened. Then to sea level rise. I told you that we were interested in high-end scenarios, because you have to know if in the most unfavorable scenario, if something goes wrong, that is very important. It may take 100, 200, 300 years. But if you make now investments in infrastructure for a future in which you know your system is not sustainable, you want to know. You don't want to build bridges and subways that are going to be not functioning in 100 or 200 years. How old is the New York metro system? More than 100 years, right? So, would you build that? If you knew that in 100 years you couldn't stay there, you wouldn't. And so we did something interesting. We asked all these climate modelers from IPCC, and we really had to twist their arms. They're not engineers, they're scientists. So we said, we want probabilities. We can't give probabilities. Okay, then please, can you give us your high-end scenario, which means that we want you to run your models and put in the most unfavorable scenarios that you still think are plausible. And this is what they came up with this gray band. Whereas this orange band, that is what our local meteorological institute gives as a sea level rise range. But the extreme scenarios, as you see over here, in 2100s, go up from 65 to 130 centimeters per century. And you'll see in IPCC report now, you'll see reflected some of these things back. Because there's such a large uncertainty still by the way, we used this then as input to another group that we said, if we get these high-end scenarios, will you look into the technical feasibility of the solutions that we use to be safe against flooding? And most importantly, can we still pay it? And they looked at it, and the good news was, it's okay. It'll cost money, but still, you can afford it. And so that made a lot of politicians happy, because we are very good neighbors with Germany and Belgium, but we prefer to stay in our country, right? And then we have another thing that we're very grateful for. If the Germans would keep to their current strategy. Again, you cannot see it very well, but we calculate, we both look at low discharge, because low is as important as high, right? Because low has salinity intrusion problems and navigation. You know, all the BMWs, Mercedeses, all these, they're all made here. And so all the steel they need and aluminum gets into Rotterdam Harbor. And we navigate it up the river. And so the Germans are very worried about low discharges because the cars will be too expensive. So if you're thinking of buying one, do it maybe soon. Anyway, so we count on lower discharges as well, but also higher ones. And this number is something that we hope we can keep, because if the Germans change their strategy with flooding, it means we will get more. Because they have not dikes everywhere, so it's great. They have retention areas. We get a high flood from Switzerland, Germany will flood, and we will have less trouble with discharge. But once they flood, you know, if it floods in the Ruhr area where the motor car companies are, they will protect themselves, and we'll get larger numbers to discharge. But this is what we count on for at the moment. Okay, so let me go to some general recommendations. So far it has been sort of like, let's say, general and conceptual. And now let's go to some more concrete things. One of the things, I told you about multifunctional, right? And I know a lot of policymakers believe that that is the way forward, and so do I. I think also that engineers, like Dave and I, we should be part of the discussions on multifunctional design. Because that's a modern engineer. A modern engineer should not sit behind the desk and wait for the terms of reference, like build me a breakwater or build me a port. We should be involved into, can we make infrastructure and connect that with other functions, not to forget the ecosystem. So we should be more forward as engineers to be part of the policy discussions. Not build me a bridge because I need to transfer traffic. No, be part of the discussion that there is a transport problem and you want to help solve the transport problem. And that's really multifunctional building with nature. And the Delta dike was something else that has to do with, most dikes are not designed to be unbreachable. Once they start breach, to limit the breaching process. Like if the breaching starts, it'll erode and erode, totally erode. But you can imagine that you build a dike that can have overtopping, but doesn't continue to breach completely. And so in Japan, they've built them. We've built some of those as well. But it's not, as I will show you, not the total solution. I cannot resist just to quickly give you a little view on the extension of the Port of Rotterdam, where nearly 90% of the outer contour is a natural dune and beach. Most ports have hard structures to protect them. Here, 90% of the outer contour is soft, and that has loads of advantages. Amongst others, dunes and beaches, in principle, follow sea level rise in a natural way. You need to compensate a little for virtual loss, but it is a very clever way. Let me further skip on that. Just a chopper view of, this was recently completed. This is now in 2010 over here. This is now closed. And this contour is all soft. And the little bit of hard structure that is there is over here. And the companies that designed it made a cobble transition over here. So I'm as happy as Larry. We don't have shingle beaches in the Netherlands. Now we have one, which we can follow. And so here's this little bit about dikes. This is, by the way, the example in Japan. So you see, it's a huge dike with even infrastructure on it. And basically, this dike is, through its internal structure and width, it is practically unbreachable. So if the water level is too high, you'll get overtopping, you'll get water behind the dike, but it won't breach and then continue to flow in. And in principle, that's a good idea, but it's not always the solution, because if you have a polder concept, like many countries have, then you can make this dike, you can make it unbreachable, but you always have interruptions. For instance, here there's a sluice complex. So this sluice over here, which is part of the chain of safety, has to have the same probability of failure as the dike. So you can make the dike very safe, but if a chain in that whole dike system isn't as safe, you have a problem. It'll break there. Let me go to the recommendations we gave for the coast. We promoted that we should not use hard structures while we can avoid it. And so since the 1990s, we have avoided building hard structures. Actually, we've been consistently taking away hard structures, because our experience is that a hard structure in a dynamic environment as a coastal system with changing sea levels is not the most sustainable solution if you can resolve it by sand. And so the recommendation was use sand, and also maybe do more with sand, even to extend your coastal system. And so one of the ideas that we came up with was, in that context, is what we call the sand engine. And it really, the idea came in the context of the fact, by the way, here's Amsterdam, Schiphol, so here's Delft, here's The Hague. In the context of, again, a minister, a woman, that said, look, if I promise that we will have an eye for multifunctional design, then, and I'm responsible for safety, but I promote multifunctional design, I should be serious about this, right? You don't just write it down into a national plan and everyone thinks, oh, well, that's very advanced thinking. And she said, no, look, if we do that, we have to make it real. So she said to all the coastal provinces, she said, you look 50 years ahead. And you tell me whether you think there's a safety problem, 50 years ahead. Can you imagine 50 years ahead? That's courageous, right? And she knew why she had to say that, because if you do multifunctional design by using infrastructure in combination with safety measures, then you talk about decades of planning. You don't talk about next year, not about the next 3 or 4 years of your election. You talk about investment into the future. So you have to make that step towards a further future. And she said, I have money for you when it comes to safety. I'll give you the money to make your coast safe for the next 50 years. And then you tell me with what functions you want to combine that. And then we have a multifunctional design. And then you have to pay for that bit, right? And then it happened that, that in this area over here, all these spots were found that weren't safe. So the minister said, I'll give you money to make that coast safe, but you come up with a multifunctional design. Now, this took a lot of discussion, and for some of the policymakers it was really frustrating. But in the end, we came up with one of the solutions, and that is that people don't like wide beaches. Wide. Like Dave told me, people don't like Virginia Beach being so broad, right? You have to walk a long way to the beach line, to the water line. And it's the same in our country, you know. They don't like that, you know. The local people say, are you crazy? Why should I walk all the way to the beach? And so the politician there that was responsible for this, he tried sort of this grand scheme of beach nourishment for the next 50 years and very wide beaches. And the people said, this lady's completely crazy, you know, we don't want that. And so what we came up in the end is what we call a second alternative to nourishment. Traditionally, nourishments are done on the shore, right? On the beach, dune maybe, a little bit in the surf zone. And then we had a time where, that started in the mid-19th, where we also use what we call shore-phase nourishments, which are at somewhat deeper water. You don't do that a lot here yet, right? Eh? But we do it quite a lot. Half of what we do in the Netherlands is on the, say, the primary bank at the end of the surf zone. Has an advantage because in the old days people used to say, aren't these people crazy? They put sand on the beach and a winter storm comes and the beach is gone. Of course, the sand is still there. It's just lying a little bit underwater because that's what nature wants to do, right? So that's why we said to the minister that time, look, just put it here. Nobody will complain. And after when the summer comes, the sand will simply go to the beach. And so discussion is over, you know, we never have that problem anymore. And then a couple of years ago, we came up with the idea that if you want to bring larger amounts of sediments to it, you do not do it linearly along the beach. Because people say, look, you widen the beach everywhere. What good is that? No, we turned it around. We said, you don't do it everywhere, but you do a mega nourishment just at one spot. And so we could convince the minister, bring in 20 million of cubic meters of sand. We call it the sand engine. That'll feed that whole coastal system in the next 20 years, and you don't have to come back. People will be happy. Kite surfers are very happy. Ecosystem is happy, because instead of coming back every 3 to 5 years to nourish the sediment, you just dump 20 million at one spot. And the ecosystem around it will slowly adapt to it, including human beings. And we did that, and it worked pretty well. And some of the benefits are, like I mentioned, it's good for nature. You have to come back less frequently. And the estimate was, it has to be there for 20 years. We'll lose 1 million a year, cubic meters, and after 2 years, I can tell you, it is nearly exactly 2 million. Here you see the construction of it. They brought in the sediment from offshore, and so they first made a very thin, like sand groin, you could call it. And here you see it near completion. There is a, this is about 1.5 kilometer. This is about 1 kilometer. There's a dune lake in it, and there's a lagoon over here. You could have chosen different formations, but that's the way we took it. This isn't even that recent, but this has developed more. And I have more slides to show you if you're interested. It's a very dynamic area. After a storm, it changes. In the beginning, we had to watch out for people not being aware of tides. And so sometimes people started walking along the shoreline, not realizing that they could end up there, and then with high water there would be a problem, because people were just used to, like Virginia Beach, right? But so far so good. We haven't had really accidents. I'm going to come to a closure. The southwestern delta, let me not say too much, but I was already a bit critical, as I told you. We used the principle of shortening the coastline, which means that we started closing over here, and when we were nearly ready to close this off as well, we got this discussion, should we not maybe cherish the mussels and the oysters that we have there, which by the way are all eaten in Paris anyway, but so we decided to put up an open barrier here, right? But that closure is sort of creating a very strong transition between salt and freshwater systems. And of course, in our economic drive, that is good, because if you have clearly fresh and salt water, the freshwater side, the farmers know there's fresh water, you know, you don't need to worry. It's not going to be salt. But of course, for the ecosystem, that's different. The ecosystem doesn't like these sudden transitions. And so there's much to say for short line shortening in an economic way, but for the ecosystem it's not that good. And so we have many problems. And so whenever I lecture in other countries that want to learn from what we do, I'm happy to tell them about our failures, because failures tell you more than success. So we're very busy trying to find, I'm skipping this. Let me end with room for the river. Some of you may have heard about it. We've had a lot of river squeeze. I don't know if you know the term, but coastal squeeze, you know. Like we narrow the transition between land and water, and we fill it with infrastructure. We built the hotels in Virginia Beach so close to the beach that there's no more beach, and we have a problem with episodic events. That's coastal squeeze. Rivers, very same. Mississippi, you name it. And so one of the big projects we have is that at more than 30 places along our rivers, let me first show you this one. This one is finished. So originally this and this were the banks. And now this whole area has been added to the discharge possibility of the river. And so the new dike is over here. And here's the sill. So under low discharge, the water will just stay here, which is good for navigation. Under high discharge, this adds to the discharge width. And of course there's water here because it's open on this side. So the water can enter, but here there is now hardly any discharge under these circumstances. And currently in Nijmegen, the largest project is on its way, and that is, some of you know DHV Haskoning, Royal Haskoning? No, it's a big consultant in the Netherlands. They're over here. This is the bank of the Waal, which is basically the combination of Rhine and Meuse. And this is now developed into an area where the river will have that additional room for the river. And that is something that I think should be, room, space for a coastal system, a mangrove system, a river system is very important. We should always question whether or not we should consider that, because that'll pay off in our future. I'll skip Rotterdam, but Rotterdam is like New York, you know, there's water from everywhere. And if you want to safeguard that, it'll take something. In the case of Rotterdam, we were thinking of, this is there, and that's there as well. This is not, this is not, this is not, this is not. We're thinking of building all this. One little problem, this doesn't exist, so We'll have to make a new river over here. And so get the water all out there. But like I said, this is very complex. These areas have so much value, but they're so vulnerable. Well, we're lucky in Rotterdam. We have only one metro line. How many does New York have? Multiple, right? Like 10 or more. And they're very vulnerable due to flooding. And I think the largest challenge that we have to safeguard the world against flooding lies in these big cities. Because it's not very simple to resolve those problems, and it's very costly as well. And then the last message is that if you basically look at what it costs, you'll be surprised. It doesn't cost a lot. But it's very difficult for politicians to score on these issues. Because if you invest money in safety against flooding, there's very little credit that you will build up. And so it's basically a political issue. And I think we should train our young people to enable them, to give them the ability to talk to policymakers and to make them aware of these things. And Dave has a lot of good ideas. We were talking about the weather channel. Oh, yeah. The weather channel should, anytime that we have a storm, the weather channel should say, look, if we hadn't had that defense there and then, it would have costed us this and this much, you know. But it's just that in civil engineering works, everybody finds it completely normal. You drive over a bridge and it doesn't break down, right? If you buy Windows and it doesn't work on your computer, you accept it. You don't do that with a bridge, right? And so there's a lot of sort of mentality, I think, and culture that we need to change. And well, that's one of the important things that I try to give to my students. And then we learn from each other. We learn mainly from the mistakes all over the world. Thank you.
So I was curious what kind of examples or arguments you used that helped people accept that soft solutions would be better than the hardened structures? Or was that difficult change?
So did everyone hear the question? Did I have to do a lot of convincing to go for soft structures instead of hard structures? In the Netherlands it was relatively easy because rock is pretty far away and it's pretty expensive for us. And we have big dredging companies. So economy-wise, it's not so bad. But I'm often sarcastic about hard structures because you'll find hard structures at many, many places around the world. And sarcastically I often say to my students, why do you find them so much? It's because for a politician, it shows like something really has been established, right? You can see it, you know, it's a hard structure, you know, and put a flag on it. It's much easier. And don't forget, and I'm being very sarcastic, a contractor earns a lot more of stone than sand, right? And it's being sold as a permanent solution. It's never a permanent solution. And so, for contractors, big business. If you look at harbors all over the world, they're nearly all hard structures. In Vietnam, I'm trying to convince the government there, you need a big port in the Mekong Delta. That's going to develop. They're going to produce Suzukis and Hondas and Toyotas there, right? Because labor is cheap and it's going to be the same like in Bangkok, you know? It's going to happen. I say, if you build a harbor there, make most of the contour mangroves. That is a natural system. There's a lot of fine sediments in the system. And if we do it correct, that'll be a beautiful natural protection. And so I hope that happens. But yeah, it's not easy in many countries. And I know here, well, Dave knows as no one else, that seawalls, well, you have Ormpilky. Some of you know Ormpilky? Right? Okay, so he hates hard structures, but yeah, he has a point, you know. Well, it goes too far, but he has a point. But I believe in seawalls. Let me be more specific. I believe in seawalls like it was applied at Virginia Beach. Virginia Beach, the seawall there is not for the structural longshore erosion. It is for the episodic event that will erode during a hurricane. And then the sheet piling and the concrete, it will limit the retreat. Of course, it'll square out, but at least you'll be safe there. But that is for the episodic events. Then I believe in it, not for longshore gradients that structurally erode your coast.
Are the other coastal European countries following the Dutch lead?
But I want to answer that. I hate answering that in an arrogant way, because you can't talk like that, I think. It's, you know, we talk to one another quite a lot. And I have very good colleagues. The guys from Lund University that gave me an honorary doctorate, they're in a country, Sweden, where they don't know nourishment. And so we talk a lot, and we try to help them to talk to their policymakers of how they can view the problem. And so we help one another, and as European scientists, we form a very good network. Even, well, you know, Spain has adopted soft solutions after years and years of having hard solutions. And they nearly have removed, not everything, but most of their hard structures. Italy wants to do it, but there's so many structures there that they don't have the money. But they are aware now that, you know, it's very simple. I mean, the coast is a dynamic environment and sea level changes. So that means that any hard object in a dynamic environment will have a difficult moment in time. And so if you can afford to do it in sediment, then it's really worthwhile, because on the longer term, it'll be much and much cheaper.
Is it easier to convince policymakers in the Netherlands to follow a strategy like this and prepare for sea level rise? Because 1953 is not that long ago. It's still in their minds. There's still a lot of people alive that remember that event. I don't think there's any problem, because we assess every 5 years whether or not the systems can withstand the design criteria. And since we have a nourishment policy, it seems the coast has gotten safer and safer and safer. So they do see that it has complete benefit.
We have obviously want to look maybe at soft solutions, so you look at soft solutions. What about the ecological pushback? Because we're going to have, I could just hardly imagine trying to put a dike across the Lynnhaven. Right?
Yeah.
Did you have those in your work, and how did you deal with them?
Yeah, no, certainly. And so this is about the ecosystem damages, and this is becoming more and more a point. Also not the actual nourishing itself, but also where you get the sediment from, because that also there you hoover the sea bottom, right, for a large area. And also during production, you have a lot of fines in the vertical. I'm very happy to see that we have two big dredging companies, Van Noord and Royal Boskalis, and they are very aware of these problems. So they know they cannot work in Australia if they don't have answers to this. So they invest a lot in how do you dredge, how do you hoover the sea bottom, trying to minimize ecological damage. And one of the things they're finding out is that in the old days, they didn't know. So they said to the government, look, we need to dredge, tell us where to dredge. And then the government would say, look, you dredge in between these yellow lines, and I want you to take away 1 meter. But now we've researched that, and we've looked at what if you dredge not uniformly, but you make sort of a hilly landscape. So you have a habitat that varies over your dredging area, and we varied that with respect to the tidal current direction. And then we monitor the ecosystem, and it appears that the regeneration of ecosystem life is much quicker, and the richness of fish sorts is even higher. And so you can experiment with those things. With the plumes, the fines, the very same thing. If you have good models, you can try to choose the moment of the tide in order to minimize the impact, for instance, in Australia on the coral reefs. And then the sand engine is an example in where explicitly the ecosystem functioning was an argument. Like, will we come back every 3 to 5 years and just nourish the same habitat region, you know, like the beach and the shore face? And so you do the same habitat region over a large stretch. Now you just dump it on one spot. Okay, you destroy everything. There's no benthos that likes a meter of sediment on its head, but it's only local. And then the sediment, as it gets distributed, it gets covered in a much more general way. And so we're monitoring, trying to see whether indeed the benthos there recovers and maybe even stays alive. And this is what the dredging companies really want, because, you know, our dredging companies wouldn't be alive if they wouldn't do that. Because you can just go to the Netherlands IHC and buy the best dredging ship there is, and you can produce a cubic meter much better than the Dutch. You know, so what you need is all that additional thinking and discussion with your client in order for you to take that.
So for a project like the Mega Nourishment Sand Engine, how many different levels of approval or different agencies or different sort of permits and funding, I don't know, approvers do you have to go through for a project like that in the Netherlands? And have you had to change the process to be more streamlined in order to do such massive projects?
It's complex. If you want to do a multifunctional design, you come across to all these stakeholders that you have to involve into the process. And well, also our country is notoriously slow in those things. Certainly projects, you know, I studied in Delft, right, which is nearly 40 years ago. Already that time, do you remember the A4 discussion? Maybe not the extension of the road to Rotterdam. You know, we're talking about 40 years, it's being built now. It took 40 years just to build a road into a system that was considered important. And of course, I mean, that started in a time that involving stakeholders was not done. And what we see now is that the hardest people to deal with are the NGOs. Because, you know, if there's a bird, and well, you know the story, right? Yes, and so what's important is that you involve those people from the beginning. And I must say, in our country, they're getting much and much better. World Wildlife Fund, for instance, they realize that they better be part of the stakeholder discussion, because in the end, they'll get out more. Right. If they're always against, of course, they may be successful in holding a project back, but in the end, you know, it'll go on anyway. So you better participate. So the message is try to involve them from the beginning and also take them serious, you know. This decision to concentrate the nourishment at one spot has been very largely driven by NGO wishes to minimize ecosystem impact and also to create an environment which has added value to what was there before. And well, in this case, we have national, provincial and local governments. And then on the local level, you have the police, you have the beach guards, you have the local restaurant owners, the local population, the NGOs, Rijkswaterstaat, you name it. I mean, it's a big circus, but it works. And we have now 3 PhDs that look at, we call this the governance problem. And so we have PhDs and we make them study that interaction between those stakeholders. What do you need to do to prevent that you don't come to a solution? And I'm very proud. I mean, we gave this advice for the mechanourishment in 2006, December. Within 5 years, it got there. And I always say, because there were 2 political champions, because you need political champions, right? If there's no political champions, it might turn out impossible. And there were 2 women. I think men would have taken longer.
I would like to hope that you would join me in giving Professor Stive another big round of applause. Thanks.